Hi, I'm Luca Villani from the Italian team, and I'm going to show you our problem, our solution to the problem candle light trick. So first of all, the statement of the problem and the trick. Maybe someone haven't seen. This is the trick. As you can see, once you blow out the candle, you can relight it, just lighting the smoke that is produced. And the problem asks us to find the maximum height, the maximum distance from this trick, and how this is affected by the important parameters, so identify the important parameters to make the trick. So the first parameter that we have found is the oxygen. Without oxygen we can do the trick, because without the oxygen we can start the combustion of the paraffin, and the paraffin is made by hydrocarbons that are chain of hydrogen and atom of carbon, and a chain of hydrocarbon needs a precise amount of oxygen to start the reaction of combustion. And once you blow out the candle, you stop the combustion. So a lot of chain of hydrocarbons don't burn at all, and we have other chain unburned that can be burned again with the right amount of oxygen in the system, in the air. And so we have to estimate, we have to stay in a position, in a condition where the oxygen is needed to restart the combustion with this unburned chain, not completely burned chain. In fact, from the reactant of the previous reaction, we can see that the ratio between the density of the wax, so the density of the hydrocarbons on the density of the oxygen, is like this, parametric formula, general. Because the air is made of 21% of oxygen, the ratio between the wax and the air that we need is, for example, for n equal 2, where we need less oxygen, is about 6%, 0.06. These hydrocarbons are, when this chain unburned of hydrocarbons are driven up by the convective motion of the candle, and this convective motion have two principal phases, two principal states, the laminar state and the turbulent state. The laminar state is the stable one, the steady state, where maybe we can find the right concentration of the right ratio, the right concentration of the wax to relight the candle, to restart a combustion. And then in the turbulent phase, the trick is not possible, because there starts a diffusion motion of the wax, so the density is not what is needed for the trick. In fact, as you can see in the laminar motion, the shape of the plume is similar at the start, for example, a lot, to the dimension of the wick. For example, so in the wick we have the right concentration for the combustion. Here we can have the right concentration for the combustion, so we can go to investigate this region and having this region. But the trick happens here. Sure. So we have we have made a lot of experiments, trying to relighting the same candle at different height, and we have this graph where you can see the number of relights on the number of tentative, so the ratio of success. And in this graph you can see that at around 15 centimeters we have quite always possible to relight the candle. Then the success rate starts to decrease. Because in its development, the smoke starts to a little bit diffusion. So the diameter of the plume increase a little, decreasing the density of the wax, the ratio between the wax and the oxygen, until a maximum height of about 30 centimeters. Over this, we can go on. The trick is never possible. We haven't been able to reproduce it. Then we can try to explain how this maximum height is correlated with the diameter of the wick, for example, in a free convectional motion, where we can take care about the ambiental condition, because they are turbulent, there are too many sources that can affect the motion. So we can investigate just how the diameter of the wick influence the maximum height. From the fluid dynamics and thermodynamics, we can arrive that we can show that the maximum height for the laminar state go like this, and for the Newton's law, the power, the heat emitted by the candle in a convective motion is like this, where H is the convective coefficient as the surface of the wick, and the delta T and the difference of temperature. And using the method of dimensional analysis of fluid dynamics, we can evaluate the convective coefficient like this, where this is a valued form, a tablet form, and this is a coefficient tablet for a plate surface meeting it. And so we can try to see if this is correct. So this dependence is correct. It depends. L is the characteristic length, but in our case we take the diameter as the characteristic length. And we take two different candles with two different diameters, and we see the ratio and this ratio, and we see that measuring maximum height for the candle 2 of 15 centimeter. This formula gives us a maximum height for the candle 1 of about 18 centimeters, and performing the experiment, we are seeing that the maximum height with that candle is about 15 centimeters. So the dependence on the diameter of the wick is respected. So the maximum height of the laminar state motion depends on the diameter of the wick in this way, in good arguments. And the next question that we can pose is, we can light a candle just in a free state. We can work on add some plugin to our experiment, such like a tube that can guide the smoke, the evolution of the smoke, the propagation of the smoke in some way, keeping the concentration more stable to make the experiment. So we tried to take the experiment, and let flow the plume, the smoke, inside a tube of a diameter of about 1.7 centimeter, and we can see that we reach a much higher height. And here there is a problem, because this jump is caused by the absence of oxygen during the propagation, because the convective motion throw away the oxygen in the tube, and the candle don't relight. In fact, you can see here where the oxygen is not necessary to continue the trick, the flame stop, and here, you can see how the trick is possible with the right amount of oxygen. So we have tried to oxygenate this tube, making slit on the tube and increasing the length of the tube. And we have this graph where the success rate increases a lot. And we can see that we have a maximum height of about 25 centimeters until 55 centimeters. We have been able to reproduce the phenomenon. After this, another important parameter came out, that is the quality of the wick. The quality of the wick, so the time the wick can give paraffin, can give wax to the smoke. After a time, the wick is not don't have enough wax to give to the plume to make the combustion, so the trick is impossible. This is our final relighting. It's very high. It's 45 centimeters. Yeah. It's beautiful. So the conclusion. The principal parameter of the wick is of the trick is the oxygen, because the phenomenon is just a combustion of the paraffin to light a candle. The plume is like a cord mixture. Okay, and the height limit is due to the efficiency of the reservoir of the wick. The wick is a kind of container of paraffin that can. Where the plume can take the paraffin to relight the candle to make the trick possible. So it is another important parameter. And theoretical treatments show that the diameter of the wick is influence the maximum height in its free development. So thanks for the attention.
So my name is Lilith, I come from the German team, and I'm pleased to make the opposition to your problem. First of all, thank you a lot for this nice presentation. The task you can see again here. What we want to stress in the first hand is that the task says that the candle has just flown out. So that's the question about the time, what we also stress and we want to discuss later. And also, of course, what's quite important is the height, the maximum height that you will also make your focus on. So first of all, what did you do in your task? What did you show us in your presentation? So you developed a theory to your problem. First of all, you showed some small experiments, some small plots, then you developed the theory. Then you also tried to compare the theory of the experiment to a certain extent. For as it was on the desk, we will discuss it, but you tried to do to a certain extent. And also, you included some errors in your theory that you explained. Also, you explained to us really detailedly the chemical behind it. So the incomplete combustion that happens here, the reaction that can, well, why the reaction can be started again, and the oxygen that is needed. So in a vacuum it won't work. Also explain the correction motion, so the laminar and turbulent state, and showed some good pictures about this. And you had nice experimental setup, so you had videos, you showed us photos, and that was quite nice. In theory, you also made predictions about maximum height and compared the different candles that you use. So now I want to go a bit more in detail to the different parts of your presentation and the things that we consider to be positive or negative. So on the positive hand, you see that you have a quantitative theory about the wax and the oxygen in the air that you made, and also the starting energy and the chemical formula that you explained and showed us. What we think was negative is that we did not see clear parameters in your formula that you can talk about, and that the wax was not included in the theory. And there are some aspects that you saw in your experiment, and we think you might not can explain with your theory, so some lacking there. Also, we missed that you didn't plot it, a difference or a comparison between theory and the parameters. You only have the numbers, but we didn't saw any plot, any graphs about this. Due to the experiments, we think it was positive that you used really slow motion analysis, so you could go more in detail, you could see more. That you observed and explained laminar and turbulent motion. Also that you had statistical analysis of the relight thing. You did more experiments, not only one. Now you explained to us that we missed in the first time because you didn't tell how many experiments you did, but after asking you could answer this, so that's quite well. And you ensured the laminar flow with your tube. That was a really nice idea. However, we think that here you can change or optimize a lot of things.
Yeah.
So, for example, also you have two different candles, so that was an important parameter for you, but we think that also you missed some parameters, or you could make more differences in these parameters. Yeah. So, negative is you missed the statistical errors. We just couldn't see any errors, but we think that just the amount of experiments you did, we need those errors. You did not consider the ambient temperature and the temperature of the flame, and could not measure it. And also you could not control the quantity of oxygen in your tube that you used, and could not control the temperature. Also, the comparison between theory and experiment that we said, we can discuss about this. So now let's come to the points of discussion. First of all, we want to discuss about the interaction between the parameters. So, for example, if you change the different candles, what other parameters are changed with this? So what is the consequence of this? Also, we want to discuss how was the setup controlled. For example, that you hold it with your hand. Maybe you can, I think you could hold it with your hand. Maybe we can improve this or find something that we can improve the setup. Did you do that's just the question, did you do everything by hands? And also the measurements, did you maybe use a program also to analyze it or to use the data? Also, if the speed of the smoke was measured, so how could you do this, or would it be useful? And the different candle materials. So, for example, the small thing that you light on the candle, was this changed as well, or what could be the effect? And the different relighting methods. So, for example, holding what exactly you hold and what exactly height. I think the height you measured really well, but the other parameters of this lighting process in detail. So I think now maybe let's go to the discussion.
Okay.
So first of all, we can talk about the interaction between the parameters.
For this answer, I have to connect my computer.
Okay,
I have a formula where you can see all the parameters in that formula. The formula is the relight number, so the parameter for the flow for the relight number, like the Prandtl number.
Yes.
All the parameters for that flow are considered there.
The
parameter that I have not considered because, first of all, some of that I haven't think about.
Okay, so you just didn't come up with?
And for the wax, we have see using a different wax for one time that the trick was difficult at different height, but we didn't have the material and the possibilities to change the wick in an easy way, to change the wax.
Okay,
to
so
change
in
the wax
a
an easy
reasonable way
to understand the difference between the wax, because we don't have the instrument, so sorry
but
for this.
But do you have any, maybe because you also stress on the chemicals, do you have any chemical explanation or physical explanation what could change due to the wax?
To the wax, it could change, for me it could change if the wax is not, the impurities in the wax for me. Because we use for example, use a wax with aroma.
Yes.
Okay, you smell it.
But do you think that has an important effect?
It's important.
Okay.
Because the wax is different. The wax is different in that case.
Okay, and because I assume that, for example, the vapor that is coming out from the wax, that this will change the concentration of the contents within this will change.
Yeah. And so the quality of the wick, the concentration, if the wick, the porosity of the wick. Yes. But we have understand this parameter, but we have found that we can't measure it or use it in an experimental way because we didn't have the.
We thought about
but
it.
we thought about it. We know that if a candle can permit more wax, more paraffin to enter. Is it the candle? Sorry, the wick, more wax, more paraffin to enter inside the wick. Probably produce more plume, more dense.
Yes,
maybe
okay, but I think
come higher.
Yes. Thank you.
I'm sorry
I think,
that you can.
No, I think, but we discussed the parameter as well. But what about the temperature? Because we discussed about the temperature. I think that this is quite an important effect because when you are in a room, for example, that is quite hot or quite cold, what could be the effect?
The temperature that the ambient temperature that we wear, where the 21 degrees. The ambient temperature.
Yes, but for example, in your tube, I think for sure you had a different temperature. You did not have the ambient temperature because it comes directly from the candle.
In the
so
tube,
do you have? But you didn't measure the temperature.
No,
in
we
the tube.
didn't measure it.
Okay. So what effect do you pursue?
For that, the different temperature inside the tube.
Yes.
How does this affect the motion?
Yes.
Okay.
For example, if you have a higher temperature, then your tube could be higher, you know? For example, if you have a high temperature, also the effect could be processed to a longer height of your tube. Or you don't think so because the vapor...
the gradient of temperature, first of all, to the question of the velocity, once that question was one of the first questions that they posed to me.
Sorry.
What is the velocity inside this laminar motion? To understand the
from
maximum
the
height where, for example, I don't know, one first idea where to make a similar analysis could be strange, I know, but like a tube where the tube is the diameter of the plume, where I have this work inside, the laminar motion. Thinking that this tube, the diameter of the tube is regular, I can calculate the Reynolds number, and when this velocity is paragonable to the velocity for the Reynolds number to become turbulent, that was the maximum velocity.
Okay, but so just to get it clear, the point here where you still can heat it, it's the laminar flow, or is this really the point where it changes from laminar to turbulent flow? Is here the point, or is it like down or up?
No, in this motion it's a bit strange because in the tube the fluid, the flow is still quite laminar, but it's in the transition state. It's not perfect laminar.
Okay.
Okay, but you don't have diffusion in this direction.
Yes, but where exactly do you have the changes between laminar flow and turbulent?
The change over here. But here, because the hair starts to perturbate, here we have steady, stable flow. Here, you don't see in the tube that the plume drive out, flow out, flow up.
But I think it's okay.
You don't
what is exactly your Reynolds number?
In a straight, what?
What is your Reynolds number that you calculated for this?
We have abandoned this idea to use another model for fluid dynamics.
Okay, so
I
you
use
just
the Reynolds number.
Yeah,
We consider this the Reynolds number for this.
But you didn't
for about
calculate it or use
the Reynolds number for this were about something of 10 to.
Oh, you just write it down?
No, 10 to 4th. I don't remember.
Okay.
First.
Okay, so the reporter correctly stated that the combustion is really important. I mean, how it's exactly the wax is burned and the oxygen is used, and why the incomplete combustion will get you your vaporized wax and you can restart it. And you presented a very good theory about the turbulence. And there was very good pairing of experimental results with predictions, because you saw that the height depends on the yes, and how oxygen depletion affects the trick with a pipe. Now you said about the wicks roll, how important it is, and you said that for different waxes we can expect different results. Now, the opponent also asked how time affects the trick, which I think is the most important question, and why the incomplete combustion can be restarted. Now, they also asked about how different waxes would affect the problem, because different waxes have different boiling points and different melting points, so that would mean that for a longer time you can produce more vaporized wax, and you can get a higher flame or a later relighting at a later time. The candle diameter was discussed, and well, she recognized the usefulness of the starting energy and chemical properties, and completed well your experimental setup, which was really impressive at the very least. But the thing is that you lack some certain parameters like the time, that's very important, and the Reynolds number, but you explained it later. Okay. And finally, it was discussed. The last thing that was discussed was the ambient temperature, which I think is not that important, but it's very. It should be studied to show that it's not important. Okay.
Right.
So, for further discussion, I would like to really ask you both, and I can move to the discussion. How do you believe that time affects the trick? Like how time affects the maximum height, and how time affects if the trick can happen? I mean, the probability of relighting the candle. So I ask first you, and then you can answer too.
Okay. So first of all, I think that time is a crucial factor, because you just can't enlight the candle and 1 hour later you can relight it. So that's why also in the task it says just after. I think that's quite important to rely on the task in this term. As I assume that you can have a higher time distance when you use the tube, because then you have the vapor just in one laminar floor. Yes, and then you can have more time between the lighting and the relighting, or the blowing out and the relighting. But where at the same time, when you don't use the laminar floor, it will take quite only some seconds until you can't relight it anymore. Also, what I assume that you have...
I will stop you now, so he has some time to...
You maybe just one thing, I think the laminar flow and the turbulent flow, when the turbulent flow starts, it will just go a bit more down, so that the relighting height decreases when increasing the time distance.
Yeah, it's true. It's correct. I agree with your explanation, but I haven't think about it.
Mm-hmm.
Yeah, it's true, really.
Yes.
Yeah, now the phase of turbulent increase and the laminar phase decrease with time. Yeah.
Yes.
I didn't know that.
The thing is,
It's not, okay, it's important.
you can actually prove that the probability, not the probability, the wax that is produced decreases exponentially with time, because that's how temperature decreases on the wick, so that you can show that way that the density of the vaporized wax higher up would be exponentially decreasing with time. So
yes.
that's
It's important.
Yeah.
You
Maybe
wanted
then-
it not so good.
Yes, but as we are on this kind of experimental setup, then maybe, of course, I said that it's quite good, but maybe one idea to improve it would be to fix the tube with some statives, so that you can fix it, and you don't have because your hand never is accurate. No, I think this would be an improvement.
For example, we are trying to do it like this, but the tube that we have used is a plastic tube. So the candle burned, liquefied the tube. It's so different.
Okay.
So we have to put it when we blow out the candle with compressed air. That's
Okay.
more stable.
And then nevertheless putting on a stative and moving it. So
Yeah.
That's the next.
We have tried to.
just an idea to improve.
Yeah, I know. But it could be useful maybe using a pipe made of
Yes, but I think it's
metal, other material.
Yes.
Okay.
But metal have a different thermal conductivity, so maybe
Yes.
the temperature inside
But
can
maybe
change.
go to another point. I think this is
Another thing, that how did you derive that maximum height? That was the square root of 1 over q or something.
Okay, or there is I cited an article. There is a reference. There is a reference, an article where this when described that there is a very interesting theory, analog to the vacuum theory for the stress of a thin straight bar. When you apply a small pressure above, this bar is curved
from the vapor. Or
this bar is curved with a wavelength. Okay, and in this case it's quite similar because we have different temperature that is kind of pressure, and the laminar flow is like a straight bar, and we have a minimum wavelength.
So
Over
you
this wavelength, the wavelength is too much that the plume starts to destroy,
so you
diffuse.
used an equivalent of this theory for your theory.
Yeah.
And so you use the article for deriving your theory.
Yeah.
Okay, but maybe also one question, maybe we have to switch to your slides, but did you have any comparison, like in a plot, between what you can predict from your theory and what you can show in the experiment? You see, because when you look on your theory, can you say, when I change this factor, this will happen, and you could confirm it with your experiments. Do you have something like this?
Teams are welcome to join.
Okay.
Maybe.
Now you can answer that question.
Okay.
I can move to the next one.
Okay.
Or if anyone has a question.
In case, that is not a completely theory, predictive theory, okay? That show a behavior of the maximum height in dependence of the diameter of the
Diameter, yes.
Okay, but what I show is just a suggestion for that. So we haven't any measure to plot the
Compare it.
graph, but
Yes.
we have shown that theory in a case where if you have seen, we have used the proportional sign. So
Okay.
the dimensional proportional.
what-
So I have make a ratio, so the proportional eliminate to test that this is real, this is
But
correct.
maybe just a really short answer. What parameters can you predict from your theory? What parameters are there included? Is there included the
The
kind of
temperature of the
candle?
hair, the temperature of the density of the hair,
What
the temperature of
temperature?
the different temperature
Okay.
between the wax
Yes.
and the hair, the temperature of the hair,
I have a question from back there. so I
and
have to
other,
check.
the diameter of the wick and something like that.
I have a question to the reporter. You had 3 plots of your probability of relighting independence of the distance. But if you try to relight the candle, it either lights again or it doesn't light again. It can't light half, meaning there should have been error bars. Why didn't you include them?
Sorry, I don't understand.
At the points that
Yeah.
were neither 1 or 0, there should have been error bars. Why didn't you include them in your plot?
It was a probability graph, so that
The
just
probability
meant
graph,
that
yeah, it will
8 out of
It's still
10
a
times.
measurement.
Well, yeah, you
He's
have to
plotting the
decide.
data of his measurement.
He's just plotting 8 out of 10 times the candle was relighted. I think that's
It's
just
probabilities. I have made
You calculate the mean value. That's
I don't calculate. I have measured. I have do the experiment 10 times, and for example, 10 times on 10, the experiment was successful. 5 times on 10, the experiment was successful, and I plotted to show a behavior of the maximum height.
You still can't exclude the fact that the true probability for this distance would have been like 0.6 if you have it like at 0.5. You can still calculate the mean aviation even though
Okay.
the things
No,
you
we
calculate
didn't.
were
Okay, and maybe to this, just was it always like not lighting or completely lighting, or were there some effects that they were just shortly lighting and going out again? Did you observe this?
Yeah, we observed that in such cases, for example with the tube, as I show you, and the propagation stopped.
Okay.
The flames started to stay, in such cases, start to stay stopped and stay blocked for some time, and that vanished. The flame.
Okay.
It doesn't arrive to the wick, sorry.
Now, I think, because, most teams did that problem, that the surface of the wick, the radius of the wick, and not the candle, is very important. How do you both think that this plays a role in our problem? The higher the surface, the higher the exposed area, so the more wax, vaporized wax is produced.
The theory used to show a behavior of maximum height, for example, for the diameter of the wick. I have first considered having the height of the wick and the diameter of the candle, but in our experiment, that's always the same. So that influenced the final result.
You saw no influence?
No, in our experiment, we have, in our measurement, our candle was quite always the same, and the height of the wick was always quite the same. In a case was a little bit different and calculated, but the difference between the two results were very low, very small, and it's not important. The main contribute, yeah, you can regulate it in the cases. The main contribute is given by the diameter of the wick.
But is it? Did you make some photos or measurements of the shape or of the kind of light that you get? Because maybe the diameter, also the height of the wick, will influence the kind of candle light you get, or is it just completely?
Okay, there's a question back there, so I can't just ignore it.
Sorry, one short question. Did you use different relighting methods? So I can also see maybe it depends on the temperature of the flame. So did you use some, for example, matches or so?
We use a lighter and a burning piece of wood.
Okay, but not, for example, some sparkles that were produced other ways?
No, we
so
have
this one setup, we focused on this.
Yeah.
Yeah, the thing is that different lighting methods.
The temperature in that case, the flame has the same temperature in that case.
All right. I have 1 minute to make conclusion.
So, thank you all for our suggestion for this for my presentation. I really accept it, and I go back to the conclusion. As I said, for me, now I understand that time is really important. So sorry if we don't have analyzed, and but in any case, the problem asks us to say a maximum height. I think that we have the best way to reach a maximum height is to drag the flow and give the flow the oxygen to reach this maximum height. You can reach maximum height if you can drag the flow higher. It's not infinite, but you can go higher probably. And the theoretical treatment was a suggestion. Okay, sorry.
Okay. Thank you. Now it's the time again. Time for the questions from the jury members, please.
So I'd like to learn how the reporter measured the Reynolds number of the plume in the pipe. And the opponent gave us some 10 directions in which this work could be expanded. So in this sketchbook of directions, I would like you to name the two perhaps more important ones.
From the directions?
Yeah, the directions in which this work could be expanded. I jotted down 10 points that could benefit from the improvement, but that's not...
Okay.
Sorry, I didn't understand.
A Reynolds number.
Reynolds number?
How did you measure the Reynolds number?
No, we don't measure it. We have calculated theoretically the Reynolds number. We have used the relight number. Relight number for the Nusselt number for the convectivity motion, and that we have measured, measuring the different temperature, different with the wick with a thermal camera that was about 43 degrees, and we have measured, we have calculated the relight number for the diameter of the wick as characteristic length, and for the height of the wick as characteristic length, and it was about it's very low the transition from laminar to turbulence, but it was for the wick for the diameter of the wick it was around UNT, very low, and for the body of the wick okay, that's right.
Thank you. Oh, please, more questions.
Yes, I think he asked me. So related on the experimental setup or all together?
All together.
Okay, so I think the first most important thing is for the experimental setup to make more parameter change and to fix the tube, that it's not influencing the vapor. And the second thing is from the theory to have the possibility to predict things from the theory that you can then prove in your experiment. So include more parameters in this.
Thank you.
Just to continue on this for one very short question. How do you think not holding the tube but fixing it will improve things?
I think that when you, for example, because your hand's always shaking and the candle or the candle light is quite not really huge, and when you have the tip here, it's not really huge. When you just shake a bit with your hands, this will make that some vapor goes on the sides, and then it's not anymore linear.
Okay.
And I think this is the most
And then I have one real question, if I may, for the three of you. Starting with the reviewer, open and reporter. There are points where you can't light the flame back, and points where you can and points where you can't. What's the difference between these points?
I think
According to the reporter. Like, what did you think the reporter thinks?
that you are certainly under the turbulent flow. I mean, you are somewhere in the transition or the laminar flow. Above that, the diffusion is really great, so you can relight the current.
I understood it, that's why I asked again here, that this point is the point where the laminar flow changes into the turbulent flow. That's how I understood his explanation.
But at the end of the pipe, the laminar flow became turbulent, quite instantly turbulent out of the flow. For example.
Okay, the next question.
All participants say that the temperature of the wick is very important parameter. And now my questions will be so that you should answer yes or no. Do you think that the thermal capacity of the material of this wick is important parameter or not? Yes or not? Thermal capacity? Yes. Is it impossible parameter the specific heat of evaporation? Is it important parameter? Yes. Is it important parameter of viscosity of liquid paraffin? Yes. Is it is it main parameter the sizes of the small holes, capillaries inside the wick? Yes.
And
where they are? Where they are?
And gravity.
I ask you where they are.
Yes, that's why we pointed out missing parameters. I think short time was too short to discuss all of the parameters. I think on the first slide it was like missing parameters. That's what I stressed also in the answer.
They are out of our presentation. Now, for example, we didn't have the instrument to use it to test that parameter. We know that the parameter is
Another
important.
parameter, surface tension of liquid paraffin, and so on and so on.
How can I change it?
But they all influence on the time when the wax is produced. The time is very important parameter, but it's combined parameter.
Okay.
Yeah.
Yes.
But this also we remark that there are not enough parameters, but I also agree that of course he can't change all of parameters. I think this would be really a lot. So maybe it would be nice to name all the parameters that you think affect it and then take out the most important ones. So where you want to stress, because you think these may be 3, 4, 5 parameters of all the 10. Like you named now, these are the most important, that's why you will stress on. I think this would improve the tackling of the problem really much.
Thank you.
So, the
I'll have time
priorities.
for one more question. If not, then let's finish this fight. And